Hello, everyone. Welcome to the One World Combinatorics Onwards seminar. Our speaker today is Vuong Bui. He's going to present work done during his postdoctoral fellowship in Montpellier on an explicit condition for boundedly supermultiplicative subshifts.
So, hi everyone. Today we'll talk about some property of basically the number of words. So we could start right away, but for I would really prefer if you can interrupt me at any time if you have any question, because my talk would be quite short. I thought I was given something like half an hour, so I didn't plan a long talk. So interrupt me at any time. So let's start with the problem setting at least. So sigma is to denote an alphabet. Um, Usually every position has a fixed alphabet, so we don't have to worry about it at all. Just a fixed alphabet of size 2, 3, 4, whatever. And we have a set of forbidden factors, like maybe finite, maybe infinite number of factors to avoid, and we care about the language of all the words that avoiding F in the sense that every element, every word in the language would not contain any factor from F. And this talk is basically about avoiding infinite um, family of factors, because otherwise, if we have only a fixed number of factors to avoid, we can basically construct an automaton and pretty much nothing to discuss in that particular case. The talk is pretty much about the paper, but I try to avoid anything complicated, and I wanted to address only the case of squares. I mean the case that the set of forbidden factors contains all the square, all periods whatsoever, and we slightly mention other results on other kind of forbidden factors, but which is just basically my talk is pretty much about the very basic ideas, and I don't want to I just want to show some proof of concept without going to details. We would not try to optimize the boundary. No constant is optimized. So three ideas will be presented. They are kind of similar to each other. One is already known, so the other two is just some extension. So some review on things we can know. So I denote C by Cn the number of words that avoid F with length n. It can be seen to be submultiplicative. I mean, submultiplicative in the sense that C of L plus M is almost CL times CM. This is quite natural. Like we every word of the length L plus M can be decomposed into the first half of the length L and the other half of length M, and each of them should be F3 itself. So we have that inequalities, and that observation is itself very useful. At least we know that by Fichte's lemma that we have the limit that the n root of Cn would converges, and it would converge to the infimum over the n root of Cn over all the n. So in other words, we pick we pick any n. We calculate Cn, and we immediately obtain an upper bound on the gross data answer. And of course, the larger n we try to compute Cn, the better bound it is. But it's only an upper bound, so we would try to have some lower bound, because we can't go so far with n, and at least we want some interval that we can prove rigorously that answer is contained in that interval, and we want that interval to be small enough, and at least we have some idea of convergence right here. So so this is not my previous slide. We have an upper bound, but this is not the only way to upper bound the language, the growth of the language. Instead of the number of Cn, we can pick any finite subset of F, of the set of forbidden factors. We take a finite subset and we build the automaton that corresponding to that subset, which is obvious that we can do it. And we just compute the structure writers of that automaton, and we immediately have an upper bound on the growth rate, because the language recognized by that automaton is a superset of the language we consider originally. And the same thing here. Instead of Cn, we try to compute the automaton for larger and larger subset of forbidden factors, and it also converges to the actual growth rate. But the same thing here, the same thing that this is only one-side inequality. So how to, with automaton, how we can establish a low bound. This is a very popular technique that built up from anyone during the years, and we can't say who is the originally behind this technique, but let's say so. At first we do almost the same thing as the previous slide said. Take the finite subset of forbidden factors and considering the corresponding automaton. So we know that there are some words that are, if F prime denotes the set, the finite subset, then we know that the automaton recognize some words that are not at all F3. Yeah, I mean, it can contain some factors, some longer factors. So we need to somehow to estimate the number of such invalid words that are unrecognized by the automaton, and we try to relate it to the original term somehow, and we subtract them and to bar it somehow. I mean, with the same automaton, we have an upper bound and also a low bound by some kind of a trick. So I try to demonstrate how can do such a thing in a similar way that we have no automaton here, no nothing at all, no automaton. I mean stateless, the stateless. But this example appears in an article of Goldenfeld, and I think it's nice. The constant there is perfect. So we fix ma with size 4 letters, and the same Cn denotes the number of square free words of length 10. And we want to prove that the ratio between two consecutive Cn is at least 2 by induction. So we already know that Cm is greater than 2, Cm minus 1 for every smaller numbers. So now we try to make a very simple observation. If V is a square free, and we try to append a letter to the end of V, then we see maybe not square free anymore, but then the square that arises must be a suffix, must end, and must appear at the end. And let's say the period of such a word is a P. P can be anything, can be even one. So we try to count somehow. Let's see, Cn plus 1 should be at least Cn times the first term is all the possible concatenation, and we now need to subtract all the invalid concatenation. And now we are allowed to erase. If we erase the second y, and we know the period, we can reconstruct the whole VC. So now we can subtract P, the period, from n plus 1, and we count all the number of lengths n plus 1 minus P. This is an upper bound on the number of possible wrong invalid concatenation. And now on the next slide, the induction hypothesis is useful now because we can bound C of n plus 1 minus B by Cn. And now Cn taken to outside, and so inside is just a number subtracted by a geometric sum, and we have a number 2 here. So I hope it can demonstrate the general ideas. And this is the first idea I would want to mention. And also we would go with other ideas as well. So in total, we want to prove some number like this. Cn plus 1 is greater than beta to Cn. So how to improve the previous slide? People often do it by integrate an automaton, like we try to have a better idea of the suffix. The more we know the suffix, the better we can choose the C here. The better we can choose C here, and we don't time the all concatenation in this way by Cn times sigma, but we put a kind of an automaton here. And the subtraction is much more tricky, but something doable here. But the thing here is our article is basically a proof of concept. So we just simply increase the size of alphabet. We don't put automaton in the article. And one of the nice thing about the previous slide is that it proved the ratio between two consecutive elements instead of proving a more practical bound like Cn is at least beta to the n. The former is stronger and is more useful in general. So now we need to have something in the beginning. In the beginning, we have shown a way to upper bound n bar in terms of Cn. And now we want to the other side of the inequality. We want a dual, a parallel picture with the automata, and corresponding to submultiplicativity, we have a supermultiplicative. So what does it look like? A supermultiplicative looks like CL plus 1 is at least CL times Cm. So now we pick a word with length L, we pick a word with length M, and we concatenate them. But some invalid concatenation need to be taken into account, and we need to subtract all invalid concatenation. Let's say U is the first word and V is the second word. If something wrong happens, it must happen around the small dot here, around the boundary between U and V, and the how to say, the square must it can be written, the concatenation can be written as x y y z with the O dot, the bigger dot, with the square y y should contain the position of dot, and we somehow need to keep track of the relative position between the small dot and the O dot, like last time with VC concatenation of a word and a letter. We kind of don't care about the right position here. We only care about the period of the square, because we know it is at the end. But now we don't know where exactly the position of the O dot and the little dot. So we need to, instead of the first sum, P sum over all the period, we also need to sum over all the relative position between the O dot and the little dot, and basically there is around 2 times P such a position, and we're allowed to delete one of the 2 y's. Among the 2 y's, we are allowed to delete one of them, and part of them belongs to U, and part of y belongs to U, and part of y belongs to V. That is why we can see C of L minus I here and C of M minus P minus I here. So basically the same idea as previously, but now we need to have a more delicate treatment and nothing very exactly difficult here. So I just copied the previous the result of the previous slide at the top. And remember that now we take the first result as the ingredient for the second result. The first result is the ratio of the 2 consecutive elements is at least beta. So now every product inside the sum can be bounded from above by beta to the period times CL times CM. Now CL and CM appears as the common factors, and we taken it out, and the same thing happens. We have a geometric sum inside, and that geometric sum, it usually converges to some constant or bounded at least, and I just rewrite it as some f of beta times CLCM. So if something depends on beta, and we wish to f beta to be positive. And in general, I just copy the previous the result of the previous slide, and well, if we want this to be bounded, we want beta to be large. And to have beta to be large, we either take automaton to improve it, or we just simply increase the size of alphabet to be 5 instead of 4. And we have f beta is a positive. So we have a form of supermultiplicativity here that CL plus M is at least a constant of CL times CM. So as we have a supermultiplicative, we have the other side of the inequality that we can bound the growth rate, not just from above, but also from below by the values of Cn. By the way, any questions, you can interrupt me anytime. So let's try to summarize everything so far. The first problem is a concatenation of square free word and a letter, and the square may appear at the end only with the conclusion that the ratio of the two consecutive elements is bounded from below by beta. And this the first problem is kind of very popular in literature. I just want to emphasize that most of the times people do it with automaton instead of this origin this origin this always simple treatment as in the example. And about the second problem is not instead of the word, instead of the second element on the right hand side, that instead of just a letter, we take it we put a word at that position, and now we concatenate a word with a word. And oh, someone in the chat. Oh, sorry. So we concatenated two words, and the corresponding result is we still do the same thing, that count all the way of concatenation and subtract all the invalid concatenation, and we try to obtain something from it. And with the ingredient of the first problem, we come up with the second problem, and the result is the supermultiplicative form. And we can see that there is a lot of similarity between the two inequalities here. So let's say in this way that the constant the constant in the second equation cannot be as good as the first constant in the equation. Well, how to say, the second inequality can imply the first inequality to some extent, because the value m can be chosen to be 1, but of course the constant times C1 can be as good as beta. But let's say we forget about constant, we don't care about constant at all, then the second inequality is qualitatively better than first inequality. And at least although the constant is not so good, but with a constant in that place, we try to obtain larger and larger, we try to obtain Cn for larger and larger n, just by a computer, and we can obtain arbitrarily good approximation of the growth rate answer. So let's try to conclude that these two inequalities are better than the inequality that Cn is at least beta to the n, if we don't care much about the constant. So now comes the third idea. What should it look like? And actually it is a word that's concatenated with itself, not concatenated to an arbitrary word. And another question is what kind of ingredient it is used. Choose the first ingredient or the second inequality as the ingredient. And the third problem is quite of curiosity, that people not only treat words as something written from left to right, but also something that can be written on a cycle, that in the end it can patch up at the top. We just write it on a cycle and read along the cycle, so any forwarding factor can be found at any position on that cycle. For example, a word can be square-free, but not square-free when we write it on a circle. On a circle, let's say A, B, C, D, E, F, A, because now the two endpoints both contains A. So if you write on a cycle, on a circle, we can see the square AA or AB, AC, D, E, F, B. And when look at the circle, we see BA as a square period too. So in general, such a word that's square free word but not square free anymore on the circle must be written as three component A, B, and C. With C rolling back to A, and CA contains a square. So, or in other words, let's write W explicitly. We have ABC. Now it means that inside the square, we have a smaller square. And actually, the notion of circular words can be related to minimal squares in the sense that both of them go the same thing and should prove such a thing. And also, Brewer Such made a question. He tried to compute the growth rate of circular words by using automaton, and he noticed that okay, it's something 1.3 both rate of square big word and square circular words appear to be around 1.3, and he thought maybe it's the same, and he conjectured it, and we can prove it. We can prove it. It's indeed the case for the alphabet size of 5 at least, but of course we can't answer for 3 or 4. We don't even touch automaton here, so we are happy with size 4 or 5. So let's go into details. Not so much different from the previous two results. We start with W, a square free, but not circular square free. And the same thing, W can be written as ABC, and now CI can be written as YY. So as usual, we try to denote the period of the square, and we know that the relative position of little dot to O dot to the big dot can have 2i minus 1 option for the position. So at the same thing, we try to constrain the period. We try to constrain the relative position between the two dots. And given those two parameters, we can delete one y out of the word W, and we can recover if we need in a unique way. So the same thing here. We let Rn denote the number of circular square words. And we consider Cn, and we subtract all invalid square free words. It's the same thing. We sum over all the period yi, and we sum over all the relative position j, and we count Cn minus I because we already delete one y, one instance of y. So the remaining number of characters n minus I. So it turns out that we used the first result, the first idea. It is quite understandable because the second and the third are not that different. So both use the first result, that the ratio of two consecutive numbers is at most beta. So now we can revert Cn minus I back to Cn here. And now we have a kind of the geometric sum here. And we know that when beta is large, then it converges. Then it's a constant, a positive constant. Yes. When sigma is large, then beta is also large. And we have Rn, the number of square free circular words is at least a constant of the square free words. So, although one is a subset of the other, both of them are not that much different up to a constant factor. And we know that one is containing in the other. So we have the obvious inequality that Cn is at least Rn. So they are in constant factor of each other. So they grow at the same rate. Of course, it didn't settle through conjecture because we try to because we fix the alphabet at the size a bit larger than we design. We wish for the case of 3 and 4 of the ternary alphabet list. Through conjecture, maybe mostly for the case of the 3 letters for the alphabet. So an unrelated remark is that it's a word is long, then square free long, then kind of a suffix and prefix is not that dependent. They're quite independent. And we can plug an automaton or something like that. But we don't really know how to do it easily. It's quite complicated. But we do want to decrease the size of alphabet. So the original articles, it's a bit complicated with with the general treatment of any kind of formula factors denoted by F. The F can be anything. So the condition is a bit technical, but you can see that it's quite the same thing here. And the size of alphabet still matters a lot. That if we can't avoid something, just increase the size of alphabet. Of course, it's very intuitive intuition. And on the right-hand side of the inequality, we can see something very similar here, a geometric sum, nothing advancing. We kind of use the same technique. We just induction here and induction that beta to minus something arises. And we did the same thing. Cn plus 1 is at least beta of the Cn. And also we did the same thing for supermultiplicative. And the interesting point here is that we can basically just exclude the equality case in the first condition to obtain the strict inequality in the second condition. And we immediately get the result. And it's quite a coincidence. We can't really explain. There are some 2 or 3 steps in calculation, but we don't quite know what is behind it. And the third result basically the same thing. Yes, we also try to write a constant. We try to write it out. Nothing fancy here. The same kind of result. Cn, Rn, and white Cn. It's quite interesting to look at that square freeness circular words, circular F avoiding words is of the same order as F free words. So let's say about what we couldn't solve. The first thing we can't really do yet. We tried a bit, but not really succeeded. So when we concatenate a word, a letter to a word, it's a kind of very common thing for the way automaton work, right? just put a single letter and single letter and single letter again, and we construct the automata. But to concatenate two words, then we kind of concatenating two states. Concatenating two states. We don't know how to do it. Concatenating two states, and then a new state arises. No, this is really hard because the concatenation of the state appears inside at the boundary of the two words. So the general form is to Cn, the number of words that we care about, the left modes and the right modes of the concatenation, not something in the middle. So anyway, just some nonsense talk about it, but I mean it's not exactly obvious. And the second thing we can't explain about the two conditions. The first condition for the first problem is here, and the second condition for the positive of the leading constant in the supermultiplicative inequality is the second inequality, and the first one is the derivative of the second one. People would expect it, but not expected. But I mean, we try, but we can't explain in philosophically anything like that. We can't really explain it to in a satisfying way. We can't really do that, and it is not clear in the proof either. And let's say about some problem we can't solve yet. And one of the things is that our technique immediately fail if the set of Boolean factors grow at the same rate as the language itself. We can prove that the set of Boolean factors cannot grow any faster than the language itself. Most of the time, it grows slower than the language. But at the sweet point that both of them grow as the same thing, our technique immediately fail, as we can see here, that f we sum over all f of the below word and the constant factor here, and beta to the minus f never can never have such an inequality, no matter what. Even we increase the size of alphabets, the thing appears on the left hand side immediately diverges. So no way we can apply such a thing. Even we try to apply, I don't know anything at all. So I find it really hard to deal with the case that the language and the Boolean set grow at the same rate. And the prime example is a language of self-avoiding walks. The set of self-avoiding walk, we can choose the set of forbidden factors to be the self-avoiding polygons. It's the same way that we can choose the set of forbidden factors instead of the set of all squares. We choose it as a set of all minimal square, which doesn't contain inside it any smaller square. So in this particular case, we don't contain any smaller cross. And for anyone work in self-walk, they know that it's not so easy to estimate the growth of the order. People always want to write something like Cn is asymptotic to alpha to n times a polynomial or something sub-exponential and look nicely, but most of the time it fails for self-avoiding walk. So at least we know that our technique has no value in such a field. And at the same time, we can see that our problem with square braid is let's say relatively easy in the sense that if Su conjecture is correct, or at least we have solved it works for alphabet subsize at this point, that minimal squares, yes, minimal squares and minimal squares grows at the same rate as circular square free words, which grows at the same rate as square free words itself. So the language of the set the minimal squares grows at the square root of the growth of the square free words. I mean, f here grows at the rate being square root of the language. So very slower, much slower. So maybe that's the reason why squares is so easy to deal with. I mean, let's try to quantify the hardness of a problem by the relative speed of the set of form factors and the language itself. Maybe it's not a bad way to quantify the hardness of a problem. And I also slightly mentioned some hasn't but not quite related problems like some numbers are naturally submultiplicative, like we concatenate something and it may something if like configuration arises. And the number, for example, the number we have considered so far is obviously submultiplicative. And we have seen that proving the other side is the other direction of the inequality, or in other words, supermultiplicativity is quite harder. And for example, let's say the norm of the power, the norms of the power of a matrix is obviously submultiplicative, but proving a form of supermultiplicative is a bit tricky. And we know about self-avoiding walk, which I have just discussed so far. No one knows how to prove something quite good about self-avoiding walks. We don't have a good a good algorithm related to alpha to the n for self-avoiding walk. No polynomial. Yeah, as much as I remember, the error term is
Looks like we lost Vuong. He did warn me that he's got a bad internet connection. So if we lose him, to just wait a minute and he'll switch to a backup. So let's just give him a minute and see if he can restore his connection.
yes. So let's try to consider something like every time we all start with concatenation, right? So in the case of F pattern avoiding words, concatenation two words may introduce an invalid word. But there is something else that quite contrary, that no matter we concatenate something to something, the result is always valid. For example, in the case of polynomials, if we're concatenating one to the left and one to the right, the result is always valid. By the way, polynomials is a set of square connected, a connected set of square on the square grid. So if we put something really on the left and something really on the right and concatenate them in a unique way, the result is again a connected polynomials. And we know that it's always super multiplicative. But proving something like submultiplicative in that case is a bit harder. Like we need to really be tricky that polynomials we need to decompose it into the every polynomial can be decomposed into two polynomials so that one is not so smaller than the other, and we need to write it in some form like at the bottom of the slide in this way. We can prove is a supermultiplicative with an error term of instead of constant, it's n log n, but it's still good enough for us to compute the code rate to arbitrarily error to approximate at to any precision we wish. So just some takeaways, not a lot. Takeaway here is that we can bound things by automaton, but also by the values of Cn itself. And the same strategy, concatenate and subtract things. And automaton and Cn seemed dual. I don't know what is better than the other. Maybe Cn provides a more satisfying theoretical result, but automaton may ask for less computation. That's my feeling. Automaton to obtain the same kind of bound, automaton to always ask for less power, computing power. But anyway, both ask for computer-assisted proof. And the second takeaway, maybe we can concatenate a letter to a word, but also we can concatenate a word to a word and concatenate a word to itself. And they all work similarly with different results. And sometimes we really want to see different results. And that's the end of the talk. Thank you.
Oh, thank you very much, Vuong. Does anyone have any questions? Hajime.
Thank you for a nice talk. And you've calculated beta for the case of square free.
Yes.
So how about the case of cube free?
Cube free, I think. And no, not well. Actually, in the article, you can see that we constructed to any kind of powers. We can even construct it to 1 point something powers, and yes, 1 point something power and any p power 3.5, 3.6. I mean, if you want to block an automaton to a cube freeness, it's a bit tricky. But if you just want to, we want sigma can be arbitrarily large, and we have the freedom to set sigma large, and we just block the formula here. Of course, if you are not careful, sigma would be large, but not too much. Let's say 5, 6, 7, 10. It doesn't go crazy to 1,000. That's 10, I would expect something like that. For Q3, if you want to, the trick of deletion is you need to be careful a bit because in the case of square, you are allowed to delete 1/2 of the squares and reconstruct the whole word. For the case of Q, maybe you can delete 2/3. Why you delete 2 y's? And it's still reconstructible, but I Matthew did to block automaton, reduce automaton a bit instead of the raw formula here. And it seems that for the case of automaton, when we plug it, we can delete only 1/3. We can't delete 2/3. So, I mean, it's a tricky. Principle works, but how it work well, it depends on how clever we are. If we try to optimize constantly, we need to be very careful.
Yes. Optimization is, of course, very difficult. Thank you.
Thank you. Does anyone else have any questions? I don't have a question, but just a comment. The one thing that I really liked was that you could do this for circular words.
Yes, thank you.
Yeah, I don't know if anyone has done that before, so that was really great.
Yes. Thank you.
All right. If there are no other questions, thank you again, Vuong, for speaking in our seminar.